In order to get an action for a massless particle, we cannot simply take the mass going to zero limit of the action of the massive particle that we studied in the previous video. So we must find something else, and this something else is an equivalent form of writing that action using an auxiliary variable that we call E. So on top of the x mu's, this action depends on a field E of lambda, on a variable E of lambda, and it has this form. X dot nu plus E m square. Okay, here in units c equal to 1. Okay, notice that this action is quadratic in the x dot mu's, which makes it much easier to quantize. Also, it admits the limit m going to 0. How do we check that it is equivalent? Okay, it is equivalent if we get the same equations of motion. So let us compute the equation of motion of the x mu's. These are very simple, so they can be obtained in just one shot, and they read e to the minus 1 eta mu nu x dot nu, and the derivative with respect to lambda of everything equal to 0. And the equation of motion for E can also be obtained in just one shot. It is a half E minus 2 eta mu nu x dot nu minus a half of m squared equal to 0. Okay, this equation for E is algebraic in E, so we can solve for E and replace the result in the former equation. This means the solution for this is just that E minus 1 is equal to m squared, m, and the square root of eta x dot. So this is the solution, and now if you go back to this equation, what you get is that the lambda is just eta mu nu x dot nu divided by the square root of eta x dot equal to 0. Okay, and this is the same equation that we obtained using the original action. Okay, the only thing that we can worry about using this new action is the invariance under reparametrizations, because clearly this action is invariant under Poincare transformations. So what happens if we transform the variable lambda into a lambda prime? We have that x dot mu is, it will be something like this. Okay, and if you go to the action, then you find that this is minus a half the lambda prime, the lambda prime, e minus 1, let's say, and eta mu nu, the x mu, the lambda prime, the x nu, the lambda prime, and then the lambda prime, the lambda squared, and here plus e m squared. So we have a problem because this factor only cancels one of these factors here, and also this factor is not cancelled by anything. But If we say that the variable e transforms as e equal to the lambda prime over the lambda e prime, where now e prime is the variable written in the primed parameter, then you see immediately that all the factors, the lambda over the lambda prime, cancel everywhere, and then you get a new action with exactly the same form as before. So the invariance under reparameterizations of the Worldline is preserved. Now we can take the m going to 0 limit, and this gives us the action for a massless particle, which takes this form. New. Okay. And if we compute now the equations of motion, the equation of motion for E to start with will give us a half of eta mu nu, so x dot mu e to the minus 2 equal to 0. So in general, this just imposes this constraint, which is the mass shell constraint in this case. This is the massless case. As for the equation of motion of the coordinates, this gives the lambda e to the minus 1 eta mu nu x dot nu. And now, as different from the massive case, there is no way to solve this equation for E, the first equation, and so in substitute E here. This causes a problem because it looks like we don't have enough equations to determine all the variables. However, we still have this local symmetry, this local freedom of reparameterizing lambda, and you see that we can choose lambda such that the new lambda prime, if you want, such that this e prime is equal to 1. Okay, you can always do that. In that case, you just get rid of e in this equation and you get the standard equation. However, if you do this in the action, you have to be warned that if you do this in this here, and you only write this eta mu nu x dot nu, well, you don't have the variable e anymore, so this constraint has to be imposed by hand because it doesn't follow from any equation of motion. Now this action is still quite useful because you see that it leads to exactly the same equations of motion. So this action and similar actions can be used if one remembers that this equation is not all the story. The equations of motion that follow from this action are not the whole story, and that one has to impose this mass shell constraint because it doesn't follow automatically from the equations of motion that that you are solving. So one last thing that I probably didn't mention explicitly when we discussed Worldlines and parameterizations. For massive particles, you have two preferred parameterizations, which are coordinate time, so lambda for a mass different from 0. Lambda can be among other things, but the preferred ones could be x0, the coordinate time, or could be the proper time. For m equal to 0, lambda can be proper time if you wish, but it cannot be, sorry, the coordinate time, but it cannot be the proper time, because the proper time would always give 0. So you compute this integral, or the integral that gives the proper time, along Worldline or a null Worldline. See that the definition of a of a null Worldline is that this eta mu x dot nu vanishes. Okay, so it always gives you 0. Then you cannot define a proper time, and you may use the coordinate time if you want, or any other affine parameter. The one that makes e equal to 1 is just not so well defined, because you don't know what was the original e you started with, so it doesn't. This is just a trick to eliminate e from the action, but doesn't tell you anything in particular. So this is what happens for null Worldlines. All lines, and these are time-like Worldlines.